Welcome to this stream today. It's 1 p.m. already, so we should get started. It's Saturday, it's been snowing outside here in Washington DC, and it's nice to be inside in the warm weather and looking at all these things with you guys. So a little bit about today. Today we are going to dive into a workshop, a specific workshop that I have created for ML.NET a couple of months ago, which touches tons of different areas while building a fraud classifier in C# and VS Code. I'm going to present this workshop at NDC London in about 10 days. So I thought it would be good for us to walk through all the steps, make sure things work as expected, make sure it works with .NET Core 3.1, which I haven't tried yet, as well as the new preview version of MLNet 1.5, I think. Which is a great opportunity to show you as well these different steps. And today what we're going to focus on is part 1 here. We're going to build the machine learning model in .NET. If you want to review this content yourself afterwards or currently, you can go to my GitHub page. It's github.com/aslotte, and you will find this repo right here. As you can see, there's multiple other parts of this workshop. We will not be touching into part 2 and 3 and 4, 5, 6 today, but I'm intending to stream the rest of the parts later. In essence, the rest of the workshop is about operations, putting it into the cloud, I guess, into a real-time data streaming pipeline, so we can do real-time inference on the fly. Part 3 here touches MLOps, which is a really hot topic that's up and coming, and part 4 touches Jupyter notebooks with ML.NET. We will be seeing some Jupyter notebooks today. As a matter of fact, we will be examining our data in Jupyter notebooks. I think it's really cool. It's using a C# kernel, using .NET Try. So I really encourage you all to have a look at that a bit further if that's something that is of interest to you. So to get started, a bit about myself, first of all. I live in Washington, D.C., work for a company called Excella. I am from Sweden from the beginning, beautiful city of Uppsala. Miss it a lot, but I also love the States. I love DC. I have a passion for machine learning, and especially this MLNet library, which I try to work with as much as I can. But from the beginning, I've been a C# .NET developer for tons of years here. So it's exciting to see something changing in this field, and we have some new features we weren't able to use before. So to get you started with this workshop, the first thing you want to do is to go into the Getting Started section right here and expand and follow the instructions. For what you need today is just installing the .NET Core SDK. You can use the latest because that's what we're going to use. I'm going to update this picture later to reflect 3.1. And then you will need VS Code as well with a C# extension. Those are the 3 kind of basic things you need here. I've decided to create this workshop for VS Code. It's just easier for conferences. It's also easier for cross-platform using a Mac or Windows or Linux, whatever you want to use. It just flows better, I think. So all the instructions will be in VS Code. So please go ahead and try that. All right, so let's dive into it. Clicking into part 1 here, we will see we have 2 different sections here. The first section is about building the model from scratch in C#.NET using the VS Code IDE. And the second part here is exploring something called AutoML. We'll dive into AutoML later, but just know that, of course, it stands for Automated Machine Learning. It's a way we can just feed the algorithms data, and the algorithms will themselves figure out how to model the data, how to transform the data, how to make sense of the data, and it will spit out different permutations with different results and different accuracies. It's just a really cool tool, and ML.NET has a tool called the Model Builder, which is a Visual Studio extension as well as a CLI tool that you can use. But if we expand the first part here of building a model, we have to kind of dive into the problem domain first to just make sense of the context here. So many of your banks today, of course, or all of your banks today, they utilize machine learning to detect fraud. Fraudulent transactions of different sorts, often in real time, to make sure that no one is using your card from another country or other states if you're not there, or using it for online shopping, which are different from your current habits. So looking at patterns. And we can do this, use machine learning to figure out these patterns, and we can figure out what's a fraudulent transaction and what's not a fraudulent transaction. It's difficult to get real data to use for these scenarios. There are of course multiple open source data sources online, such as AWS Open Data, Google Public Datasets. I definitely recommend Kaggle, which is a machine learning and data science competition platform. But even those don't have an abundance of real fraudulent transactions, mostly because it contains personal information, of course. You don't want your account number or credit card number or amounts just floating around there. So the data we're going to use today is based on a Swedish PhD. I think it's from Kalmar University. Can't be completely correct there, but it's using generated data. So data that is as close to real data as possible, but it's synthetic. And it works perfectly for our scenario. So in any machine learning, anytime you're building a machine learning model, there are some steps you need to follow. First of all, of course, we need to understand context, but then we need to understand the data. What's the data? Well, how does the data look like? What's the column? Is the data clean? Do we have any missing column, missing values? Are there any outliers? And so forth. What are we trying to model, right? So that's the first thing. We want to explore the data. When it comes to something like this, or in a real-time scenario, the data can be very large. We're not talking about 2 megs here or 3 megs, we're talking about gigs of data or terabytes of data or petabytes of data. In our scenario, it's not huge, but it's still 500 megabytes of data. And opening something like that up in Excel is not going to work. Excel is going to crash, it's not going to load all the data rows, it's going to complain, it's going to be slow. So what do people do instead of using Excel? Well, if you look at the Python world, the real data science world, most people use pandas and they use Jupyter notebooks, or they use some other way of loading data in memory and exploring it programmatically, instead of just using Excel. As of, I believe, November of 2019, ML.NET has now support for Jupyter notebook support. So there's a C# kernel, which means that you can program your own models in Jupyter notebooks. You can also load them in Jupyter notebooks, and you can explore the data there. You can do things like charts and tables, all kinds of cool stuff, which really helps with this data exploration phase. And that's something that has frankly been missing from the start, but I think now it's quickly catching up. So what I've done here is I've created something called My Binder to host Jupyter notebooks for anyone willing to explore the data. It's possible to follow this link right here. It will start My Binder with a Jupyter notebook that I already created, with different steps we can execute to explore the data. If you're interested in that try, and you're interested in how this works, you can definitely go to the .NET Try's GitHub repo. But in essence, what I've done here is I have 2 files here. I have one Docker file and I have one NuGet config file that are being used to create this My Binder. The Docker file, of course, explains, details out all of the things I need to install in my container to host this Jupyter notebook, and also explains from where you should get the Jupyter notebook that it's going to display. And the NuGet config just tells us where to find the different dependencies. You can go into My Binder after that. You can kind of, I think you just define where your repo is, and it will automatically start a notebook for you. So if you click on this link, you end up coming into something like this. And let's see, I may have to restart this. Let's restart it again. It's good. You can, maybe not go away from the repo though. Let's see, to explore data sets. All right. So this is pretty good actually. We'll see when it starts here. So it takes us to the My Binder page, and it's starting this repository right here. And I was actually, before starting the stream, exploring some issues I had with this. It's moving very quickly, and there are a lot of breaking changes that can happen. So you have to, if you start hosting these Jupyter notebooks in My Binder, you have to make sure you keep your Docker file up to date to point to the right dependencies, right versions, and so forth. But now I think it's working. So as you can see, this is a Jupyter notebook, and it's completely okay if you're not familiar with this. I was definitely not familiar with Jupyter notebooks for quite a while, but what you can see here is that you have different cells, right? So this is a cell, this is a cell, this is a cell, and so forth. And you even have, okay, in this case we don't have any text cells, but these cells are so-called code cells. But you can also have markdown cells or other things, and I actually never seen heading here, which is cool, but obviously you can do headings with markdown as well. The cool thing about Jupyter Notebooks is that you can execute each cell independently. So if you start by executing this one, we hopefully will be installing the NuGet packages required here to use. So you can see here we're installing the Plotly NuGet package 2.0, and we're installing ML.NET's 1.4 NuGet package. And since we don't have I don't think we have, as of this stream, a general availability version of 1.5. I think it's only a preview version. I'm going to leave it to 1.4 for now, but we will update it later. So let's see. Okay, it's spitting out some things, but it's done. So you can tell it's done because you have a letter of 1 here. If it would have been a star, that means it was still executing. So we know it already installed the NuGet packages here. So that's awesome. So doing that, we can continue executing the next one. And the next one, what it's doing is going to a URL here that is hosted in Azure actually, and it's getting the data to be used for our analysis here. In our case, I'm not going to pull down 500 megs of data into my binder because it's not going to be able to handle the load. So I have a smaller version of the data available that represents the same data. So it has the same kind of proportions, has the same cells, same columns, and so forth. It's only 28 megs of data. It's going to be easier for us to handle. So after we have put our data locally in this container in our working area, we have to define various things here. If you skip this a little bit first, what we're trying to do here is that we're trying to use ML.NET to load the data in a shapeform form and display the data for us. So we have to define how our data looks like. So without looking at the data file, I can tell you all that we have these properties here. So we basically have a class, just like Entity Framework, with tons of properties. We have different values for them. What you note directly, I'm sure, is that we annotate each column with column name and load column. The column name is strictly not required, but the load column is. Load column will tell you what the index is of the data. So we know that step is number 1, type is number 2, it's obviously serial indexed, and so forth. So step is a time measurement. It's not minutes or anything. It's like 1, 2, 3. It's just when the transaction happened in time. Type is what kind of transaction we had. Is it, I think there are cash out, cash in, debit, those kind of things. Obviously the amount is what amount. Name origin, so that's the account number where the transaction is coming from. Name destination is where it's going to. And then we have the balance on the starting account, and we have the balance on the destination account, and then we have the change here in between, so the new balance of those accounts. We have 2 flags here as well. It's fraud and it's flag fraud. It's fraud is what we would call a label. So all of these things up here are features. And in the data science world, what we're trying to predict is called a label. And we currently have one label, and it is fraud. All right, so we're trying to detect, and this is what we're trying to detect, right? We can ignore is flag fraud here. For the sake of completion, we're going to include it, but this one is not very reliable for our data set. All right, so we're going to load in this one. We're going to say, okay, please define a class called transaction. We have all these columns. All right, so we definitely have an issue here. That's good in some ways, and also interesting. So we also, it seems like I'm missing one thing here, and I know what I'm missing. I'm surprised that I'm missing it. I guess we may have got an error here actually. So I'm missing these two here, especially the data one. But let me execute that here. This is great. This is why I'm running this, so I can figure out things here. So you will see that we were missing the namespaces for these attributes. So let me write that down because I do want to fix that. Let's try to run this again to see if we have an issue here. Okay, that was working fine. That's working fine, and we already have it on file. Okay, I'll take a note for later to look at that. That's fantastic. Jupyter notebook. These are the things I want to find before the conference, of course. Okay. In that case, after that, we're going to load a file from text file. And in ML.NET, we use something called MLContext to load, to kind of define all our operations. MLContext is like a DB context. It's just where all the operations reside. So if we create an MLContext, we can go to the data catalog and we can use a method called load from text file, which takes the path to the file, if it has headers or not, and how it's separated. It also defines a generic schema, which we have defined above. So if you do that, we're going to load in a reference in memory here, data view, that we can use later. And by using that data view, we can then just use some methods on the object to take the first 5 rows of this context here. And obviously, we already seen those run before here. We see that we have this data. So this is how the data looks like. We have the steps, of course. We have payment, transfer, different types of transactions. We have the amounts. We have the name of the accounts, and so forth. And it's flagged true or false here for if it's a fraudulent transaction. Perfect. So we see a couple of things directly. If we want to use this in our model, we do need to transform it. ML.NET does not like strings. It can only work on numeric data. It's something that is something to remember. Kind of down those lines as well, you can see that I've used floats instead of ints here, or doubles for a lot of, decimals for a lot of values. For example, these could have been decimals, they are currencies, but we're using floats. And I think I even used floats for the step here, which is obviously an int. And the reason I'm using floats here is because that's the numeric definition in ML.NET. If you try to use something else, you're going to get tons of errors. So just use float or a single here, and it will work fine for you. All right. So the last step here to explore our data is to get a chart of our data. So we're going to use something called Plotly, which is a third-party library, which currently doesn't have any real good C# documentation, but it has really good F# documentation to get an understanding of the distribution of the data. So if you look at the data here, we see that we have 99.9% of our data is not fraudulent, so 401,000 rows. And we only have about 0.5%, I guess, not even that, less than that are non-fraudulent. So this is an issue. We have highly skewed data. We have data that is not equal in some ways, and if you train any machine learning model, it will be very good at guessing non-fraudulent, because if it guesses non-fraudulent, it will be correct 99% of the time, even more than that. So that's not very helpful, because of course it's great to have a model that is accurate 99.9% of the time, but it's not very helpful because we'll miss every single transaction that's fraudulent, and that's the whole point of this machine learning model. So we will see later in this workshop how we can tackle that and things we can do to make sure that that's not going to be an issue. All right. I hope that was useful. So we have been able to explore data now. We have seen the structure of it. We have seen the distribution of the data. So if we go back into our instructions here, we have done 2.1 now, and we're going to continue on 2.2 here. So let's see, 2.1, we're going to do 2.2. So let's get started with ML.NET, okay? The first thing we're going to do here is make sure that we have a solution created, more or less. Doing this requires that you've already cloned the repo locally and put it on the C drive under a path like this. MLContext real-time data streaming workshop, and you create an empty catalog called workspace. Workspace is going to be where you're creating your solutions, where you're doing all the fun stuff, right? So let's work on that. So we will open Visual Studio, VS Code here. We'll go to a new terminal, Control-Shift, comma if you want to. And I've already navigated into this folder, but if you're working on your own computer, please go ahead and write CD and then the path to this workspace folder once you have cloned the repo locally and put it under that location. All right. And I did not intend to do something here. Okay. Let's see. Hopefully that didn't crash anything. Okay, good. All right. So once we're in that folder, we're going to create our solution here. So we're going to create a solution to train our application, and it's going to be a console application, right? Just like before, you have that new console to create that, and we'll name it Fraud Prediction Trainer. Hit enter here. We are hopefully going to get some stuff done here. Okay, perfect. We'll see we get a solution or a product right here. Store succeeded. Nice. All right, perfect. So we have a simple console application created. We have our product file here. We see we're using the latest at this current time, 3.1. So far looks good, right? So if we go back here again, the next step is to go into this created folder here. I'll go ahead and copy all these instructions, mostly because I want to make sure they are correct and there's no typos in them. Oh, actually, it's installing some stuff here, so we have to wait. Okay. That is good. Time for me to get a water then. Well, this is good. That definitely is helpful for me to do before the workshop going live. Dun, 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 dun. All right, so we're gonna go in there, and then it's time to install some other things. So basically, while this is installing, what we're trying to do here is we're going to create a console application that will load the data. It will transform the data, so get those string values to something useful. It's going to select an algorithm to train a model on. We're going to train the model using that algorithm. We're going to evaluate the model for accuracy, and we're going to see how we can improve it. And then eventually we're going to save it to a zip file, which is going to be the final product of this machine learning model. We're going to do all of that in VS Code. We're going to do all of that in a console application. And you will see kind of how simple that process is once you get a hang of it. It's the same structure for more or less any model you're trying to do here. Okay, perfect. Not now. So let's go in here. Done that. We're in there, and while we're in this folder, what we're trying to achieve here is we're going to install some NuGet packages that we need. We'll start off by installing the main one, which is Microsoft's MLContext package here. And remember before I had some typos here, so it's good if you copy and test this. So it's going to restore that, and if we look at the product file here, we see we have installed 1.4, and that is the currently latest available version. I was hoping we'd do the preview version, but I realized it's a preview, so it's not going to be installed by default if I don't ask for it. But that's okay. I want to make sure we use what is latest here. So MLContext team, please don't do any breaking changes before now and NDC. That would be very useful. Oh, sorry, that was not what I want to copy. All right, so we need two more packages here. Those two packages actually contain algorithms that we will use. The first one is going to be fast. The first one is not FastTree, but that's going to be the last one we use. But we need that, and we also need the light GBM package here, which is going to contain I believe the first algorithm we're going to try out. Okay, perfect. We have that all handled. We are good to go. All right, so we're going to open up VS Code in this area. We're going to reuse the same IDE version here, same window. We'll just go ahead and go straight into this one so we can see different folders here. Okay. I should probably have clicked yes before. I should have read my own instructions, but that's okay. All right, so we've seen the content of the file is looks like this. Well, kind of like this at least. We have the new versions of everything, which is great. I have to take a new screenshot of that. I'll make a note. Perfect. All right, so we need to have the data file now, and we need to have it as part of the solution. So we're going to make sure we take the data file and we put it in the folder where the solution is. And if I'm not mistaken, I have the workshop cloned on my desktop here, and we have the data right here. And you can see I have a small one for exploratory testing, but I also have a large one that is almost half a gig. So I will take that and I will go to my C drive, and I will go to where I have my workspace, which is here. And we have our just created trainer right here. And I believe I should put it right here. Okay, we'll copy that in there. So the next step here is to make sure that our data file gets copied over when we build our solution. So when we build our solution, we want it to be copied over so we can use it. Okay, perfect. So we can use it for predictions. So we're going to copy this item group in here like that. Ooh. And that's just going to make sure that the data file we just copied over, ooh, don't want to do that, it's going to be used when we train a model. Okay, and you can see now that it looks more or less like this, so we are pretty good to go. Okay, and now we're going to open a new terminal window, and we're going to go ahead and build the solution and make sure things are not broken yet. If this works, we should be good to start coding. Okay, build succeeded, 0 warnings, 0 errors. That's the way we want it. We like that. We'll go back and continue. All right, so the first thing we want to do here is we want to create an MLContext. And I think I explained that previously, but an MLContext is where all the methods resides that we need to train a model. So we'll go in and change this to a new MLContext. Right, and when we have MLContext, we do need to add our namespaces. Actually, not sure if I can do that. Yep, nice. All right, just control and dot, obviously, just like in Visual Studio, will get the namespace you need here. So what is an MLContext? Well, an MLContext has different catalogs on it. I think catalogs is the name the ML.NET team wants the community to use. We have a binary classification catalog, we have a multi-class classification, regression, clustering, blah blah blah. And each of these, of course, is its own ML task. And you find specific things in trainers and evaluation methods under each of these catalogs. You also have some more generic catalogs, such as transforms and model. This one has save operations and load operations for a model. This one has data operations on the data to make sure that we have something useful before feeding it into an algorithm. All right. So if we don't do that, and if I don't do that, perfect. If I go back to my program file here, we're going to start to load our data. And let's go back and copy this so we make sure everything looks okay. So if anyone is wondering, by the way, seed 1 is really only needed when you train a model. You don't need it when you load your model again or load data. But seed 1 makes sure you have deterministic randomness. It makes sure that when you split your data in a training set and a test set, that it's going to behave the same way when you run it again and again and again. So why is that important? Well, we definitely don't want the model to improve or deteriorate just to run when you run it again in the same code. We want it to be having the same behavior over and over again. And seed 1 makes sure that that's the case. All right. So we're going to continue here. We're going to load our data. To load our data, we will need the path to the data. So we'll put the path, I believe, here. And that's not what I wanted to have, of course. I'm not sure why I put it there. It should be within the class. Perfect. All right. So we have a data path, and we would now need to define our loader here. So before we can load the data, we do need to create a class that holds our schema. So if you remember where we did a Jupyter notebook file here, we did have a schema that we need to define before we load the data. There's nothing different with, in this case, we need to make sure that we have the schema defined. So what we're going to do here is we're going to go back to our folder where we have the program file, and we're going to create a new file here. And the file is going to be called transaction.cs, and we are just going to copy this file straight in here. Perfect. And you can see it contains the same things as before. Just make sure that we have a proper schema, and remember, load column is more important than the column name, but we'll have both in this case here. And also remember float and not decimal. It's super important. I can't count the number of times I've torn my hair off for that scenario before I've remembered to do it all the time. All right. So once we have our schema, we can then load our data. And we'll load our data by copying in this statement here. So what are we doing here? Let's make this a bit smaller. So we're going into our MLContext, into our data catalog, and we're using something called load from text file with our generic schema data path to load our data in memory. There are different ways you can load your data. Text file is one. You can load it from a enumerable. You can create your own data in memory. You can load it from a database with a SQL database adapter, I believe. And I also think you can load it from Parquet. So text file is probably one of the more common ones, but if you're using enterprise transaction systems, just know whether you can load it straight from tables or views, or you can feed in your own SQL statement to concatenate your own data set. There's lots of possibilities. Perfect. So we have our data, and we have it all good. And we look like this. So perfect. The next step here is to split our data. And we want to make sure we have about 80 to 90% of our data in a training set, and the rest is going to be in a test set. So why do we need that? Well, the training set is used to train a model and make sure we get something that is reasonably accurate, while the test set holds us to the truth here. It makes sure that we haven't overfitted our data, so it fits the data too much. So overfitting is making sure it's a process where we make our model know the training set inside out, but it's terrible at predicting new incoming data. A test set is data we kept from the side, away from the model, so that when we use that to make our predictions, we can determine if the prediction it made was close enough to the real value that we already know. So test set obviously has the accurate true value, and we can make a calculation of how far away it is. For example, if we got 8 out of the 10 rows in a test set correct, we would have 80% accuracy. So we'll go ahead and copy this row, and we have a method in MLNet to split the data for us automatically. Train test split does that. It has some overloads, as you can see here. We can define our test fraction ourselves. By default, it's 10%, but we can make it 20 or 30 if you want to. That's something that you would have to try yourself to see what works best for you. Cool. All right. So we have split our data. Now we want to transform it. I'm not going to read all this text for you, but in general, there's a few things we want to do here. First of all, we have the type column. The type column contains things such as payment and debit, different types of transaction. We can't use that straight out of the bat because ML.NET or any machine learning model don't understand strings. We need to be in a numeric format. What we can do is we can use something called one-hot encoding and transform that column to binary columns that does one-hot encoding. So for example, we'll have a column called is payment, and that column will either contain a 0 or a 1, and for each type of transaction we'll have a single column to use. This is very useful when your cardinality of your column is low, so like 4 or 5. because you don't want it to create too many columns. The more columns you create, obviously the more memory footprint you will have. You have issues with out of memory exceptions and so forth. But if you have something like 4 to 10 different permutations, then it's just fine. Just use that. There are other ways of handling just like infinite number, I guess, of string values. You can featureize the text instead, if it's words, for example, that you're using in a column, or you can use labels instead for different values. Labels are good, but some models are sensitive to them because it's hard for them to determine if one is better than a two. Sometimes it makes its own assumptions there. But we'll go ahead and use type here. So before we start doing that, actually, I want to follow down, continue down this line here. So that's the way we'll transform the type column to numeric columns. The second thing you want to do as well is to use the name of the destination account. So the name of the destination account is probably useful because it's likely that one fraudulent activity will be followed by other ones. It's possible that they will go to the same account, right? The name of the original account is probably not very useful because, frankly, anyone can be a victim of a fraudulent attack. So the destination account is probably very good to use. You see here that we use one-hot hash encoding instead, and that's because the cardinality of this column is kind of endless. They have so many rows, and each of them can have its own unique value, so we run the risk of getting an out-of-memory exception here. But if you copy this row to our solution, we create something called data processing pipeline. The data processing pipeline is nothing else than just appending different properties by themselves here. Appending different actions. The first one is transforming the type column. The second one here is appending the one-hot hash encoding. And I see directly here that we are missing something here. We are missing, I think we're actually, we're missing that. We're missing a semicolon here. And let's see, are we adding anything more here? Okay, we are actually adding more here, so we do not want a semicolon here because the final thing we're trying to create here looks like this. So what are the things that are left here? Well, we don't need to transform any more of the columns, but we do need to decide and tell the machine learning model which of the features we should use. Remember, you don't need to use all the features in the data set, you just need to use the ones that you actually care about. In our case, I would say that the ones we care about are type, name of the destination account, the amount we're transferring, so is it a large amount, small amount, and the different destination and origin balances here, and some other things. This is of course kind of a guessing game. Not really, but it could be a guessing game. There are methods you can use to explore the data to find these intrinsic relationships between the data, so you can make a more qualified guess. But in the end of the day, you can add and you can remove columns from this feature vector to get a better result and a better, more accurate model. But we'll go ahead and copy this instead, which contains the full transformation and the full data processing pipeline. All right, and we could use, I'm sure the question you have right now is, why are you using static strings here? Why don't you use the name of the property? Yep, that's correct. In an ideal world, we could definitely use something like this instead. Type. So let's actually go ahead and do that, and we can change the instructions here because it's a little bit prettier. And I can't believe I forgot that name dest. And see if that works. So that's type, perfect, transform those two. We want to transform the type here as well. We want to transform the name dest, right? So copy this one and we'll say name dest. Use the amount here. It's good practice to do this instead because you never know when you change these column names, and it's kind of going to be an issue overall here. All balanced dest. And if you have any questions as I do this, feel free to ask those over the chat, or if you have a question later, you can just contact me on Twitter or GitHub. I'm happy to answer those as well. New Balance origin. And the final one, I think, is New Balance destination here. And I think we do have one too many of these. Or was it one too little? Okay. Okay, so I didn't change this one because obviously that's nothing we have in our schema. And the features column here is something you just need to use more or less. You can call this whatever you want to. You don't need to call it features. So this is the feature vector, right? That's the kind of combined product of all the things you want to use for a model. But I do recommend you use features because if you don't use features, you need to override tons of methods further down the line here. So please use features as a default value. Okay. So let's go ahead and maybe copy this over into the instructions here. This is a good thing that we can do right now. Please bear with me. We'll duplicate this one. And let's see if you can find it. This is after that instruction. And it's here, I think. Okay. And I think we need to definitely change some more things here because we do have these other ones here. So let's go ahead and do that as well. MLContext. I believe this is an issue. Let's see, why is it not? I see. Well, that's good to know. Okay. Does that look good to you guys? Features. Looks pretty accurate. We would have that for the concatenate function. Okay, perfect. And we'll go ahead and change the data processing pipeline as well. We would need to do the type and name destination here. So let's do that. That would be, I think, the whole text right here. Actually, we would need to have this right here. And I believe we have enough. We don't have enough. Now we do. Okay. And we'll just go ahead and fix the last one as well to make sure it's accurate in case anyone wants to copy these instructions. Okay, perfect. So let's go ahead and commit this. Use the name of method or property names. Too long. Alright, so let's refresh this and make sure that looks correct. I'm the worst person ever to review my changes before committing it, especially since this is my own repo. That's a bad habit. I should definitely not do that. But yep, looks pretty good here. That looks good. That looks good. That looks more accurate. And if we go ahead and copy this in, I just want to make sure we don't have any compile issues here. We'll take that away, add this in. Yep. Looks good to me. Alright, thank you for bearing with me there. I just want to make sure we update things as we go along. Alright, so we have created our data processing pipeline, right? We have massaged our data. We have done things we want to get done. And now it's time to actually choose the model, the algorithm we want to use to train our model on. So this is the step that I think a lot of people get caught up on or think that machine learning is all about. There are tons of algorithms out there you can choose to train your data on. Of course, like linear regression, nearest neighbor, naive Bayes, and so forth, especially decision trees, are very common ones. But just know that picking your algorithms is kind of a guessing game. The more experience you have, the better you're going to get at finding the right one quickly. But at the end of the day, you usually want to try 5 or 10 different ones anyway, to see how the data behaves with those different algorithms. So in our case, we have something called binary classification. Binary classification is an ML task. Multi-class classification is another ML task, and regression is another one, and so forth. With binary classification, what we're trying to do is just determine one out of two values. In our case, it's true or false if it's fraudulent activity or not. But given the binary classification ML task, we have limited our scope of what algorithms we can use, okay? And we probably limit it down to like 10 at most, or something like that. So it's not as many as you may think. And if you are interested in knowing which ones you can use and what they do and what they're good at, because they're good at different things, there's perfect documentation on Microsoft's documentation. There are also other types of documentation you can go look at. In our case, we're going to use something called a logistic regression, to train our machine learning model on. And we'll create a training pipeline based on the data processing pipeline that we did before. So if you look at the flow here, we load our data, we split it into a testing and a training set. We feed our data through our data transformation pipeline to massage different values, and then we create a data processing pipeline based on a training pipeline based on a data processing pipeline, and we'll go ahead and append a logistic regression for operation here. Note that this method takes only one real value, and that's what the label column name is going to be called, and we have it as is fraud. And again, as I did up above here, we're going to update these instructions here to be a bit nicer. We'll use a name of column, name of method here, and we'll pass in transaction and is fraud as the property we want to use. Okay. Let's go ahead and update those instructions real quick. Get the duplicate here. This should be a quick one. Way past here. Okay, perfect. So we'll do that. I think we'll put it slightly to the left here. Good. One in, so it's treated as code. Okay, that's fine. And once we have created our training pipeline, we can use the training pipeline to fit our training data. So this is the kind of the magic step that you need to use, which is super simple, but we have built up everything for this moment. We're taking our pipeline that includes the data processing pipeline, call a method called fit, we pass in our training data set, and we get a trained model. That's kind of as simple as it is. And the trained model is going to be the one that we can then save later, and we can use to evaluate the model on our test data. Okay, so let's look at that a little closer here. So we have our trained model. What are the next steps? When are we done, right? Well, the next step is going to be to evaluate the model based on the test data, to see if it's accurate or not. And after that, we want to save the model to zip file so we can use it in the cloud or use it somewhere else. But let's start by evaluating the model to see how accurate it is. And we can do that by transforming our test set and getting predictions for our test set. So remember that we have our test set on the side, it's about 10%, and we know the correct answer for each row in the test set. But we're going to let the machine learning model here that we have created guess what the correct prediction is going to be. So we're going to get a list of predictions here. It's going to be treated as an iData view, as a lot of other things in ML.NET. And based on that, we can calculate metrics. And metrics is the accuracy, something like F1 score, recall, precision, different machine learning words and terminologies that we can kind of explore a bit later. But the evaluation method resides on the ML task. Just remember that. So if you're doing binary classification, we also need to use the same ML task for our evaluation. We pass in predictions, we pass in the label column name, and again we're going to use the name of method here to make it a little bit less bulletproof. And I think we need one more of these. Too many. Great. Let's go ahead and update those instructions. That's why I left it open here. And that would be this line, I believe. Okay, perfect. Let's go ahead and save that. I don't think we have too much else right there. Okay, let's commit that. Go back. Perfect. So let's take a moment and see if this works. So if we go ahead and put a breakpoint here, we should be able to run this method right now, run this whole machine learning model training, and we should be able to get metrics. So let's put a breakpoint up here, make sure that we get this kicking off, and let's press F5 and let's debug this, just like any other console application. Let's see if it's starting up. Or not. All right, starting up, perfect. Getting our debugger up and running. Nice, and we got a breakpoint. So it's going to take a little while to load the data and get everything going. And it's going to, the thing that's going to take time is the fit method here. Because this is, before that we're just using in-memory things, we're not actually loading the data, we're just building our schema and everything else. But when we hit the training method here, or the fit method, it's going to take longer. But we had an issue, and this is good. This is the things I want to find before it's too late. And, oh, this is great. All right, so this is another reason why we shouldn't use the name of, well, this is a reason why we shouldn't use the name of properties. So if you remember here, MLContext is case sensitive, okay? So the name of the columns are actually called type. And if we start changing that to type here, we're going to have an issue. And I believe it's actually sensitive to headers in general. So we have two options. One is to change all these to uppercase, and also go ahead and change the data file to have all the headers in uppercase. Or option 2 is to go ahead and go back to not using what's it called? Name of. But let's try real quick here to use uppercase. I'm not sure it's going to work, but it would be nice if we used real names here. I think if I do this, it's going to just say that it can't find the columns in the dataset, which is fair. But it's a good experiment to see if we are binding only on load column or also on the name of the column. All right, so let's save all of those. Save all. And let's try this again. If it doesn't work, what we're going to do is we're going to roll back the changes to the transaction file, and we're going to revert our changes and not use name of for now, at least, to make it simple. Okay. Okay. It's taking a bit more time. That's nice. If this works, we definitely need to update the transaction class to be up to date here. This is going to take a minute or so, I think, to get it working. Okay, it's looking promising for sure. It's definitely loading the data now. It's using the pipeline, so it seems like it's able to find these columns and properly use them. I'll go back here in the meantime. I like it though, if that's the case. That means that this will be easier in the future for me. Okay, looks like it's working. So I'm going to go ahead and update, before I forget it, the transaction class here that we use for our description, just to make sure we don't break anything for people doing this workshop. So I'll go ahead and copy all of this, remove it, paste this in. We'll just verify that this is how it looks like. Okay, looks good. Nice. All right, let's go back. We are moving along in a nice pace here. So let's go ahead and transform the data. And if we now look at the metrics here, let's see, it's taking a little while to calculate those metrics. We should be able to get accuracy and other things. Perfect. All right, so we can see here, and we have unfortunately the bug statement in the way here. Let me see if I can go further up. We can see that we have an accuracy of 99.8%. That is fantastic, but it's misleading. Why is it misleading? Remember again that the data is highly skewed. So 99.8% of the data, or something like that, is non-fraudulent transactions. So if the model was just about to guess non-fraudulent on everything, it will be pretty accurate and we'll get an accuracy of this. So it's not so helpful. So what else can we use instead to evaluate our model and see how good it is? Well, we can use something called F1 score, which is a harmonic mean between recall and precision. And recall and precision are two measurements that measures false positives and false negatives. I believe that recall, and I may have to refresh my memory here, recall measures the false negatives, I think. Maybe it's the false positives. But in essence, it's what it's trying to do is to figure out out of the whole population that we have made a prediction on, how many of the fraudulent transactions did I miss? Okay. And precision is the opposites. It looks at everything we predicted and say, okay, how many of the ones I predicted were actually not fraudulent, or were actually fraudulent. So they are by themselves opposing forces. And actually, to make sure I say the right thing here, and I do need to refresh my memory myself, let's look at instructions, because I do believe I have written that down somewhere. Okay, perfect. So precision here attempts to answer the question, how many of my positive findings are actually correct? So, for example, yeah, and the recall here is how many of the actual true positives are actually correct. So recall takes into consideration false negatives. So meaning in our case of fraud transactions, those are the things we didn't catch. Perfect. Yeah. So recall is trying to figure out, okay, how many did we miss, right? And precision is trying to figure out, okay, of the number of ones we actually said were fraudulent, how many were actually fraudulent. So it's trying to find the false positives, while recall is trying to find the false negatives. And we want those to be close to 1 as possible. And F1 score is kind of a good harmonic mean between both of them. And in cases where we have skewed data, the F1 score is really important to determine how good our model is. And if we look at our current model, I believe we should have something of 0.48. Yep, if we round it up, that's 0.48. We should be close to 1 as possible. 0.48 is not a good value at all. So we do need to work a bit harder to get something useful here. And we can also look at the confusion matrix. The confusion matrix can be found here. It's really hard to read from this kind of setting, but I have pulled it out and put it in the instructions. And if we look at the confusion matrix, we can see that the predicted values are in rows, while the actual values are on the y-axis here. So we said that 650 were fraudulent, so actually what I'm trying to say here actually is that we want all the values on the diagonal here. We don't want any values here. If we have a value here, What does that mean? Well, it means that we thought it was not fraudulent, but in essence it was fraudulent. So these are kind of all the false negatives, right? So we have 1,200 cases where we actually missed the fraudulent transaction. And we have 155 cases where we said it was fraudulent, but it was not fraudulent. So it's a false positive. False negative, false positive. It's a little bit difficult to remember, even for myself, and it's good for me to refresh this as well to make sure I'm up to date. All right, good. So we can kind of conclude that this model is not great. We need to do something better. So how can we do something better? Well, we can use something called decision trees instead. So again, there are different machine learning models that are better at skewed data than others, and one of those machine learning models are decision trees. Decision trees just handle that skewness a lot better. We're going to use something called a fast tree binary. That's binary trees. So each kind of node only has 2 leaves underneath it, and then that one can have 2 leaves underneath itself, but it can't have more than that, which limits how much it can overfit the data itself. And remember, we don't want the data to be very good at our training set. We also want it to be good on our test data set. So what we'll do is we'll copy this and we'll go ahead and change our current trainer and see how that changes the behavior of this model. So we'll go ahead and change this step right here, our training pipeline, and see if that I can't copy the whole thing. Maybe that was a good thing I should be able to do. And we'll say, okay, it's this step right here actually I want to change. Perfect. And I definitely have too many parentheses right now. Label column name. Okay. And maybe I want too many here. And we also need to add a using statement here. And let's see that I made that clear. Yep, I made that clear. And let's go ahead and change this as well, so we don't have an issue. This would be transaction is fraud, and that's features. Nice. So let's go ahead and just change this real quick before I continue, and then I will explain what this does. And that should be here. I'll just change this line right here. Okay. Fast tree binary. Okay. So what is it doing here? Well, we're saying to use decision trees, and specifically a fast tree binary fast tree. And we are saying that you can at most have 10 leaves, so kind of 10 nodes, 10 levels down. We are also saying that you can only use 50 trees. So what this is kind of a random forest. It's creating 50 independent machine learning models, so 50 different decision trees. And it's using that to create something called an ensemble learner, which is a bunch of weak learners, but together they are a very strong learner. So think about it as a group of people. One individual may not know all the answers, but if you have 50 people in the same group, they can all work together to figure out what the correct result should be. It's the same thing with this kind of random forest, or a forest of different trees. So I believe we should debug this now and see. So if we run this again, put a breakpoint here, yeah. All right, let's do that. Let's run it again. I'll keep my breakpoint there because I just want to make sure everything is working as intended. Alright, so this is going to take a little longer because we are actually creating multiple models, each of them that are a weak learner. So I believe it takes about 1.5 to 2 minutes to do this on my PC, but I may be wrong. So wait and see there. It's been great so far, being able to update the instructions to be more accurate. The decision now is to update the screenshots or not. It's definitely more work. I think I may leave them as they are, but who knows? That may be something I want to do later today. Alright, it's running. Let's wait and see. Currently working on this. Yeah, as you can tell, it's taking a bit longer, which is as to be expected here. So if you have any suggestions, by the way, for this stream in general, or ideas of things you want me to explore, I do have a suggestion box as part of my channel. Don't be afraid of leaving some suggestions there as well. I regularly review that box, and I will definitely take those into consideration. All right. While that's running, let me see if there's something I want to do. Do need to take some screenshots, I think. Will be useful. Make sure to refresh this and make sure that the change I've done so far looks good while I wait. That looks good. I think I had some more changes up here as well. Nice. Okay, looks good. Wow, it's taking a lot longer than I thought, actually. But it's running. Just taking a while to complete. So once this is done, we're going to I believe look at how to save it, and then we're going to switch over to look at how we can do the same thing in a lot less time using something called AutoML, which is a really cool CLI tool that I hope I have installed on my computer, and if not, you will see how to install it, which is useful. And I should probably consider reducing the number of trees here to something more reasonable, given that this is taking a lot longer than I thought it would be taking. Okay, we're gonna let that be for a little bit. I'll continue to the next section for now, and let's see if that completes by itself in a little bit here. So what you will see, at least, and we'll definitely make sure we follow along here so we don't so it works, is that you will see that we have improved our F1 score tremendously. if you remember before, we had an F1 score of 0.48, I think. We want to be close to 1 as possible, but that was not just acceptable. But by using decision trees, we get a model that is a lot better, and it's at 0.84, which is it's a really good result for this model. If we look at the confusion matrix for this model, we will see that it's also improved. Remember that we want all of our values on the diagonal, because that means that what we predicted is actually what we expected as well, right? Is fraud is here, is not fraud, and it's not fraud. So we have reduced our false negatives here to 21, and I believe before we had 1200, and we've also reduced our false positives here to 202 from a little bit more than that. Not tremendously, but what we want to do here is really reduce the false negatives, because we want to make sure we find all of those fraudulent transactions. And again, that's kind of the balance between precision and recall. You can improve one a lot usually, but not the other. So in our case, we favor precision over recall, and as such we get a much better false negatives value. Good. So I don't think I have instructions on how to save this, which is interesting. That means that we'd never get it down here. So we definitely need to add instructions on how to save this. Maybe it's in here. Okay, good. It's in here. I can hear my computer working hard here, which is good. All right, let's wait with that. But in general, when you save this, what you do is you just call a save method on the model catalog. You pass in your train model, the schema, and the location where you want the file. And in the end, you're going to get a zip file to use. So that's awesome. But we're going to move on and see if we can train our model using automatic machine learning instead. So what is automatic machine learning? Well, it is a way to use different tool that you can also have as a Visual Studio extension to automatically train your model. To do that, we can open up a new terminal window here. So let's try that. New window. This other one is highly used here. Let's see if you can get that smaller. Okay, good. Open up that. We open up a new terminal. And we'll go back and navigate into our trainer catalog. And we're going to use the same data file now, and it's possible it's locked because we're currently training our model on it. So let's see if it works or not, but I'm not sure if I expect this to work. But before we do that, we want to make sure we have the tool installed. And the tool is called MLnet. And in the getting started instructions, it will explain how to do this. But if I just type MLnet, we'll see if this is something it recognizes, and yep, that is recognized at least, which is good. So we'll go ahead and copy this command. So this command, what it's doing is saying use automatic machine learning on this dataset that is currently in this folder. Remember, we copied it over earlier. The label column name is fraud. The max expiration time is 120 seconds. It has headers, and we're using binary classification. This is obviously way too small for a set of half a gigabyte, and you can tell that by the fact that we're trying to run one method, and it's taking a lot longer than 2 minutes. But for the sake of demonstration, we're going to try this, and we'll see if it's going to break or not. Okay, so it's working on the first iteration, and it's loading the data. And given that it's working on both things in parallel, it's possible that it would not complete. But in general, and we'll definitely see in 2 minutes, it's going to spit out a list of different algorithms it's already tried, and it's going to spit out the result of those algorithms. And I wonder if I have that in my instructions on how that's going to look like. You can see here what it's doing, right? But let's wait for a little while here to see if that works. I'm still surprised that this doesn't work. I do need to go back to this one and see if I need to adjust the number of trees here. Because that should work. But it may be maybe that I'm streaming at the same time as I'm trying to train my model, that it's just too much for my laptop. Okay. But let's go back to the second window here and see how it's doing. Okay, still working on that. About 30 seconds more to do before that is complete. 15. Can't believe this is not completed yet. To me, it's a big surprise. All right, let's see what we have. It's possible that we actually won't have a single model here, honestly. Yep. So you can see here that with time expired before creating a model, we always need to try more than 120 seconds to get this to work. And I think it's probably because I'm streaming at the same time. I usually get one model, so this is a bit surprising to me. But that's something you have to try and make sure it works. Same thing with this case right here. But I won't waste your time on this stream to try that. But just trust me, I guess, that that's going to work. We'll pause this for now. I'll have to look at this later and see what's going on. All right, but in essence, automatic machine learning will give you tons of different options. It will not only give you models that you can try, but it will also give you solutions that you can use to as a seed, I guess, to further adjust it and make it more accurate. I definitely encourage you to check out the automatic machine learning part. I think it's really cool. It's something that I use a lot just to get a good feel of the data, and it's something that's going to be up and coming. It has a Visual Studio extension that you can use to even do image recognition and other tasks, so definitely check it out. All right, so with that, we have walked through part 1 of this workshop. We have created a machine learning model, and what we'll do in the next streaming session, not right now, is to create a data streaming pipeline. So what we want to achieve in the end is that we want to put our machine learning model into this real-time pipeline as an Azure function, and we want to allow it to infer predictions on incoming events from an event tab and put it back in an event tab, and then using Stream Analytics, we are going to put the Power BI dashboard up and take other actions on that data. But again, that'll be for another streaming session later, most likely next week. And with that, I thank you very much for joining today. I hope you learned something. If you have any questions, any concerns, let me know. Please send me an IM on either Twitter or LinkedIn or GitHub, whatever works for you. If you find something that's not working in this workshop, please open a PR for it if you have a fix, or just an issue if something you want to ask. That would be awesome. I appreciate any contributions to this repo. All right. Well, thank you very much for joining today, and I hope you have a great weekend.